To find the relationship between concentration and absorbance, our group used an amine stock solution substance to create 3 dilutions to put into a spectrometer. Through this, we found the absorbance of each solution and used those values to find their concentration. Each dilution had its own unique concentration. In the lab, the stock solution we produced had a concentration of approximately 0.02 molar. We did this by dissolving 0.125 grams of copper sulfate pentahydrate in a small amount of water. Once dissolved, we added 1 milliliter of concentrated ammonia, causing our solution to turn a clear, dark blue.
To prepare our dilutions, we first set out 3 beakers. In the first beaker, we added 3 milliliters of the stock solution and 22 milliliters of water, creating our first dilution. For the second dilution, we added 3 milliliters of the first dilution and 22 milliliters of water in the second beaker. For the third dilution, we added 3 milliliters of the second dilution and 22 milliliters of water in the third beaker. To calculate the concentration of dilution 1, we multiplied the concentration of the stock solution, 0.02, by the amount of stock solution we put into the beaker, and then divided it by the total amount of solution for the first dilution, which was 25. Our concentration was 0.0024. To calculate the concentration of the second dilution, we took the concentration of the first dilution, 0.0024, and multiplied that by 3 because that is how much of the dilution we put into the second dilution. We then divided this by 25 because that was the total amount of solution for the second dilution. This brought our answer to 2.88 times 10 to the negative 4th. For the third dilution, we multiplied the concentration of the second dilution by 3 and divided it by 25, getting 3.456 times 10 to the negative 5th.
With all of our dilutions made, we filled a cuvette with each of the 3 dilutions as well as 1 for the stock solution, 1 for water, and 1 for the unknown solution, being careful that the solution was right at the line. We took each of the cuvettes to the spectrophotometer. For this lab, we used the spectrophotometer to determine the relationship between concentration and absorbance as it scans each of the solutions across all wavelengths. Using the spectrophotometer, we can determine the solution's lambda max, or maximum absorption.
Absorption and concentration have a positive correlation, and we know this because of the Beer-Lambert law. The amount of light absorbed is directly proportional to the concentration of the solute in the solution. Beer's law is represented by the following equation. E is for molar absorption, which is a measure of how well a species absorbs any given wavelength of light. This can be determined by rearranging the equation or by looking at the slope of the graph with absorbance over concentration. C is for molar concentration or molarity, which is calculated by dividing the amount of moles of a solute by the total volume of its solution in liters. L is the optical path length, OPL, which in terms of the Beer-Lambert law means it is the distance the light travels through the sample or solution in centimeters.
Here's an example of a graph scanning across all wavelengths. The lambda max is shown for the solution throughout the highest peak. To scan our sample across all wavelengths, we took the absorption of our stock solution as it was the solution included in each of our dilutions. Before we found the absorption for the stock solution, we put our blank solution or water into the spectrophotometer to zero the machine. It is important to zero the machine because as it resets the absorption baseline and takes into account only the copper mean, the absorbances will be more accurate. Finding the absorption of the stock solution helps us identify the optimal wavelength for obtaining the absorption of our dilution samples later on. Our graph had a peak at 560 nanometers.
We then opened the Simple Reads application and set our wavelength to the optimal wavelength of our sample, 560 nanometers. We zeroed the machine with our water and then took the absorption for each of the dilutions, the stock solution, and the unknown. For scanning the wavelength and finding the absorbances, we made sure to wipe the sides of the cuvette facing the beam. We pressed the read button and found the absorbances for each sample. All of our absorption values are as follows. We then created the following graph. As shown, there was a positive linear relationship, and we found the following equation. Y equals 0.2974x plus 1.0851.